This is a story about an Arduino sketch that will listen to a port or a wire and record the number of clock rises that are seen on the wire. More specifically, it will record the time in between successive clock rises. And based on the time between successive clock rises, it will estimate the frequency of the clock signal you're supplying. I don't have a clock generator with me right now, so I'm using a Grove button, which is made by the Seed company. Here's a picture of the button. It attaches to a chassis, and an Arduino can read it. So, at any rate, so I'm using a new construct, which is a pound define. So this is a C preprocessor idea. And the idea is if you have some parameter that never changes in your code, but might change from compile to compile, you can just use this pound define. And so that does a simple search and replace before the program is compiled. And wherever it sees num points to average, it will replace it with the number 10. Wherever it sees include serial prints, it will be replaced with 1. So that's a new construct. It's useful. So inside of the code, I'm reading from a clock pin. So that's going to be digital 8. I've got some int variables and some long variables. The int variables will store the clock signal at various times. These times will store the millisecond value on the the microsecond value on the microsecond timer inside of the Arduino or inside of the Atmel 328. That microsecond timer rolls over like every 70 minutes, give or take. So I told you about the preprocessor, that pound define. So now I was on my way to printing conditionally. And so as long as that include serial prints is 1, this piece of the code will be included. If it's not, if it's 0, this piece of code will not be included. So if you want to have a debugging switch that turns on all kinds of prints, a pound if, notice bracketed with the pound end if, is a nice way to do it. So we'll be watching clock pin, so it will be an input, and we need to, so the T values are timers, so we need to record the microseconds. And just get an initial value in there. So the printing and statistics at the end of this program take some time. And so the reading looks for a pattern, but the first instance of that pattern is thrown away. So if we're trying to record 10 intervals between clock rises, we're actually going to have a cycle that has 11 clock rises, but the first one will be thrown away because I'm assuming it's a regular clock source, and I don't want to include the computation time to do a bunch of serial prints in my program. So I read this pin, so I read the clock state, and then I wait a millisecond, and then I read the clock state again. Notice this puts an upper bound on the frequency we can read. We wouldn't expect to read something faster than maybe half a kilohertz with this delay. And so we're looking just for the rise. So if this is low, and if this is high, again, if not S1 and S2, so if we have low, high, and so if the clock pulse grows and we haven't found one yet, so found one is initially 0. Can you see that anywhere? Yeah, initially 0. So if we haven't found one yet, we will store the time that was observed at, and then we will never enter this again by switching this found one to true. So this clock won't start. We compute a DT and we throw it in this time array and we reset the index to 0. Note that index is initially 0. So times is an array of maybe 10 points. But here's the thing. We want to throw this data away. So we compute it, and then the next time, so then if else, right? And none of this happens because it's if else, it's exclusive. So the next time we see low, high, found one will be true and not true is false, and so this will not be done. And then we'll enter this else block, which looks busy, but there's not a lot going on. So we record the time that the clock rose. We find the difference in time between now and the last time the clock rose. We call that dt. And we store that in an array. This is an array of long things. And then we count it. I was 0, now it is 1. So we're getting ready for the next time we see a rise. Now, when I get to 10, or however many points you want to average over, when that happens, all of this averaging stuff happens. So we've got sums for the time, we've got sums for the square of the time, and we print some information, how many points are we averaging, and then dt, right? So we're going to print out dt. And there's more than one dt, there's 10 of them. But inside of this for loop, right, I equals 0, I less than 10, I'm going to print out each element of the array with a space. And then down here, I get overflow if I'm trying to multiply, like 70,000 seconds by 70,000 seconds, right? There's a lot of overflow that happens in here. So I actually turn these long times into millisecond times. So they're initially microsecond. I turn them into milliseconds by multiplying by 1,000, and I cast them as float. So that's just an effort to reduce overflow. I don't like that, because then my answers are garbage. So the sums are actually floating point sums. There's no point in doing double because the Atmel 328 doesn't. Well, it's really the Arduino language that doesn't do that. You could probably have a double precision library. It would be slow. So I compute these time sums and these time square sums. And then when I'm done, I compute an average dt and an average dt square. So this is all of the dt's squared and averaged. I divide by the number of records. A statistician would call unhappiness on this because they actually believe in dividing by n minus 1. Let's not talk about it. So once all the statistics are done, we have a carriage return, and then we print out our results. So the time sum, the time square sum, this is just for debugging. Then we have the average dt, right? That's actually something we care about. What's the average time in between clock pulses? And the 6 is 6 digits of precision. And then we need to print out the plus or minus. So the plus or minus is something called the standard error of the mean. So on the top, you should recognize the standard deviation, right? Because you've got dt square average and dt average squared. The difference square rooted, that would be sigma. And remember, sigma over the square root of n, remember the square root is here, is the error. So the standard error of the mean. So that's what this is all about. We print it out. Finally, I need to compute the frequency. Remember, this whole manipulation is in milliseconds. So I need to convert into seconds. So I multiply by 1,000, divide by dt. And I also can compute an average standard error of the mean of the frequency. And so that is this calculation right here. At the end, you just reset I to 0, you reset found one to 0, and you roll over this T0. So the code then looks like this. Whoa, here it is. I'm going to push the button a bunch of times. So let's look at this. We're averaging over 10 points. These are our time intervals between clock rises. And notice it's a human pushing the button, so it's very far from regular. My time sum is 1800 milliseconds. My time square sum is computed as well. My average dt is about 180 milliseconds. And there's an error in that, right? 180 plus or minus 12. And that is a frequency of about 5.5 hertz, plus or minus about 0.4 hertz. That's it. That's the story. So this example is meant to make it easy to, or easier to interrogate the mystery source. So there you go. The code will be on the course website.